Hello, everybody. Again, I'm Brynna Downey. Thank you all for coming. I'm part of the Southwest Research Institute. This is some work that I've been doing with Robin Canup as part of the Survey Chloe team. So I'm going to be sharing with you an updated model of lunar accretion. So in the canonical giant impact theory for the formation of our moon, a Mars-sized protoplanet Theia collides with the early Earth. Right, a little high latency. And then this collision forms a debris disk that is composed primarily of melt, and which settles into the equator plane of the Earth. Impact simulations can predict the bulk properties of these disks, like the mass, the angular momentum, and then we take these bulk properties and they become the initial conditions for our disk that we feed into our accretion model. We form the moon. So we have one criterion for forming the moon, and that is to make a moon with the right mass. It's the only thing on our wish list, our only goal. And then from there, we identify exactly where in the disk that mass came from. This is to help with the interpretation of the elemental and isotopic compositions of lunar samples. Diving straight into our accretion model, we're looking at a cartoon edge-on view of the protolunar disk. Earth is at the center. We have three main components. You have solid particles in the outer field. We call them moonlets. Interior to the Roche limit at about 3 Earth radii, Earth's shear forces are so strong that any solid object will be completely torn apart. This has some heating associated with it. So any mass interior to the Roche limit, we treat as a fluid melt. When this melt layer gets heated, inevitably, it'll form a vapor atmosphere. Now, previous accretion models have assumed that convection in the vapor and melts would completely vertically mix these two components. So you would have kind of like a hot foam, but then it was shown that the melts would still rain out and settle into the midplane. So this is what we're updating to our accretion model. We're treating the vapor and melt as two stratified, physically separated layers. Okay, so the moonlets we advance in time with an n-body code, and the melt and vapor with analytical equations. Onto some physics. The moonlets will interact. They'll merge, grow, scatter. There's a viscosity with the melts, so you're going to have viscous heating and also spreading. So the melt spreads outwards and also inwards. So it'll dump mass onto the Earth constantly. It's the main way that the melt loses mass. When viscous heating occurs, it'll evaporate part of the melt up into the vapor atmosphere. At the same time, the vapor is cooling, so some bits will condense. We track that exchange of mass between the two layers. This is a fun one. Sometimes moonlets are in resonance with a location within the disk. There's a torque, so the inner disk will be radially confined, and then the back reaction will push the moonlets outwards. Okay, then lastly, when the melt viscously spreads beyond the Roche limit, we take the bit of mass that's kind of overhanging, we remove it from the melt and make a couple new clumps and turn those into new moonlets in our n-body code. All right, so that's our accretion model. You've seen everything. So what have past accretion models accomplished? Well, for starters, for initial conditions, they assume that most of your initial disk is within the Roche limit and this melt vapor part of the disk. They then feed that into their models, and they find a very clear trend that less than half of any disk goes into the final moon. All the rest of that material is lost due to viscous spreading onto the Earth or scattered to space. All right, so to make a lunar mass moon, when you have a less than 50% accretion efficiency, you need at least 2 lunar masses of material in your initial disk. However, because there's always a however, canonical impact simulations produce disks that are between 1 and a little over 2 lunar masses. So to make a lunar mass moon, you need at least 50% accretion efficiency. So how do you get more than half of any disk into the final moon? Well, this is a feat that hasn't been accomplished by previous accretion models. We have to do something. To make a long story short, our stratified vapor melt layers, we thought that would be a solution. It wasn't. Two different effects canceled out. So we were left with no other option than to challenge the assumption about the initial conditions. So to kind of question how was the initial mass radially distributed within the disk. And this is actually quite straightforward. You look at published impact simulations, and there are very few that have actually published what fraction of mass is outside the Roche limit and what fraction is inside. But when they do, they find that more mass is beyond the Roche limit in this field of moonlets in 48 out of 51 of the cases. So this assumption that most of the mass is inside the Roche limit, not valid. Furthermore, having more mass in the moonlets completely solved our accretion efficiency problem. You get more than 50% of the disk into the moon. Now I'm going to show you a successful case. We make an excellent lunar mass moon from a disk that started off being less than 2 lunar masses, greater than 50% accretion efficiency. More than 80% of the disk is initially far out in these moonlets. The other 20% is in the melt and vapor. This is a snapshot at 2 days. On the x-axis, you have distance from the Earth, y-axis height above and below the midplane. I'm showing everything here. You've got the Earth, melt in orange, vapor blue, Roche limit, 3 Earth radii, particles are circles. The height of the melt and vapor is not physical, it's just a proxy for the mass. It's been 2 days, and this large circle is what will be the final moon. It's already at 65% of its final mass. So it was more productive in 2 days than I've been in my entire life. It's cleaning up. It is accreting rapidly. So that's why it's so important to have a large supply of mass in this outer disk. Now you're going to watch a simulation. All right. Within a year, the moon has either accreted everything it can or it's scattered it. The melt is viscously spreading. It's dumping material to the Earth, so the vapor is replenishing the mass. Oh, look, it's reached the Roche limit. It's spawning new bodies, new moonlets. Some of them are being accreted by the moon. Most are being recycled back into the melt. But the main effect of all of these new spawn moonlets is to scatter our big moon further out in orbital distance. And because of that large distance, most of these new particles aren't accreted. Okay, so if you look at how the final moon's mass increases with time, log scale on the x-axis, I don't even bother showing you 0 to 1, because in 4 days, the moon's at 95% of its final mass. It is rapid accretion. It gets a little bit more mass by a month, then it stalls because there's nothing out there to accrete. It has to wait for the melt disk to viscously spread to the Roche limit, spawn some new bodies. The moon gets the last 2% of its mass. What's the takeaway? 98% of this moon is from material initially outside the Roche limit, placed far out there after the giant impact. Very cool is that it's the first time a lunar mass moon has been accreted from a disk with realistic post-impact properties. It wasn't the only successful case. You need at least 1.4 lunar masses in your disk, and you need at least 60% of that to be in this outer moonlet field. So in conclusion, you can make a moon if most of the mass is initially outside the Roche limit in this field of particles. This is a feature that is in fact predicted by canonical impact simulations. Our new treatment of the stratified vapor melt layers, it didn't hurt, but it also didn't help making the moon. We're still glad we did it. And then lastly, we rapidly accrete the moon in a matter of days. So very little material has come from the inner disk, which would have equilibrated isotopically with the Earth. But that happens over a period of 100 years. We accrete in days. There's some isotopic implications there. All right, I'll leave it at that. Thank you.